We're starting off with Aconity3D, teaming up with our Thomas Grünberger from nLIGHT Plasma. So we're welcoming Marco Beckers. He's working in the testing facilities of Aconity. He's a process development engineer and he has great results to present. So please give it up for Marco Beckers.
Thank you, Andreas, for the kind introduction. Today I want to talk about the beam shaping laser AFX from nLIGHT, and actually it's a transfer from cubic simple samples to real parts. And it's a continuation of last year's project where we extensively investigated the AFX beam shaping laser, and I'm really happy standing here again and presenting this topic. I want to start with a brief introduction of our company, Aconity3D, what we are and what we do. After this, I want to explain the working principle and the properties of AFX and give a short recap from last year's outcome from the project before I hand over to my colleague Dr. Thomas Grünberger. And at the end, I want to give some productivity and economics aspects as well, and give a short summary. So Aconity3D, what we are, what we do. We are a LPBF machine manufacturer located in the most western part of Germany, near Aachen. And our mission is to accompany our customers on their way to additive manufacturing. By the right consulting, identifying the customer needs, the individual needs, by carrying out feasibility studies, process developments, and run some small series productions for evaluation purposes. That's our mission, and therefore we offer some quite wide range of modules. So starting from our 5 machine basis, the customer can configure their machine completely on their own by choosing separate process chambers, different process monitoring systems, or heating modules up to 1200 degrees C preheating. But focusing more on the process side of view, I guess everybody knows that LPBF is in general a very complex process with interactions of various physical phenomena like absorption, heat conduction, or evaporation, which is not fully understood right now. But as a machine manufacturer on the one hand and operator on the other hand, it's our passion to ever better understand this process and to influence this chaos in our favor. And one way to influence this is the heat source, the choice of the heat source, and for example with the AFX beam shaping laser with 7 different intensity distributions. Besides the Gaussian one, the common Gaussian one, the operator can use the ring beam and 5 more intensity distributions in between, differing in the ratio of power between center and core. And so the operator is enabled to not just only print filigree parts with high precision, but also mixed geometries and optimized parts, but also bulky parts with a high productivity. One important purpose here, or one important thing here, is that you do not need any additional setup to shape your beam, but that you can vary your intensity distributions on the fly within the process. And to investigate this innovative laser, we ran an extensive and broad parameter study in last year's project. And the aim was to investigate the isolated influence of the beam shape on the material properties of Inconel 718 and the mechanical properties as well as the microstructure. So we used the defocused Gaussian one, the ring beam index 6, and one hybrid form with a power ratio of 50-50. And due to time constraints today, I would like to invite everybody interested in this parameter study to join me after this presentation for a short discussion. But as a summary, as you may see here, we were able to tune our texture. So the defocused Gaussian one led to a weak texture, whereas we have a really sharp texture for the index 6. And this came by the formation of different melt pool shapes. So we have shallower and wider melt pool shapes for index 3 and especially index 6, which led to a less competitive growth of the dendrites and therefore more epitextural growth of the grains over many layers, leading to this sharp texture. And the mechanical properties of the sample of index 3 and index 6 outperformed those of index 0 in terms of ductility, what you can see on the right side, and whereas the strengths are comparable. These values are always comparable to conventionally manufactured Inconel 718 samples by other machine manufacturers, but while maintaining part quality and with a higher build-up rate. So we had a little bit the case of invention being the mother of necessity. So we had to think of a potential use case to be sure that this is not only applicable to small cubic parts, but also to complex geometries. And then we thought of the case of printing turbine blades, since here the crystal growth parallel to the build direction or load direction is beneficial for the use case. We printed it with the defocused Gaussian one on the bottom, the index 3 in the middle, and index 6 on the top. And what you can see here on the right side of the EBSD images is that we were able to reproduce those results in a complex geometry. So we have the weak texture for the area of index 0 defocused, and the sharp texture for index 6 with highly elongated grains along the build direction. And that was really great, since we had it reproduced with complex geometries as well. And to get more details about the process itself, I would like to hand over to my colleague, Dr. Thomas Grünberger.
So thanks for the impressive results. As you know, nLIGHT Plasmo is dealing with process monitoring. There are several possibilities of process monitoring. You find some of them on the slides. Perhaps you find some of them you are already using. The interesting thing is Aconity has a very special opportunity to add your own sensors to their box. So they deal with the data registration. You get really out of the machine the layered graphics, the pseudo-layered graphics of the different sensors. So you can add your own sensors. What we did in this project, we used existing sensors of Aconity, especially here the parameter 1. So we have a parameter at 30 kilohertz sampling rate using sensitivity in the area up to 1700 nanometers. Means we can detect radiation, infrared radiation of, let's say, about 300 degrees of Celsius using the sensor. So we get out layered images, and you can analyze these images layer per layer. So you get one image per layer, and what you can see here is the temperature distribution for the example before of one layer, and you can directly correlate the different sensor signals to the EBSD image. That means yes, we have sensors and we can calculate KPIs which correlates to the microstructure, yeah, that works great. But the interesting thing is you can do this layer per layer, but you can do this also for the complete volume. And that's a new approach. So we have the possibility to do this for the complete volume. So we analyzed now one part. You see on the right side the standard CT analysis. So you have this ISO rendering where you can really walk and look inside the part by changing thresholds. On the right side, you see we change the opacity in different temperature areas. So you can look for in this case, for example, for the substrate, and you can also highlight overheating areas. In this case, we had an OK process, less overheating areas, so it works okay. And you see here on the right side a flaw. We don't have the parts here because it's used for destructive testing, but we found a flaw which is really in the part. And on the right side, you see that's also possible using this software and to clip through a part. Yeah. So hopefully I could show you how you can use or give you added value by using monitoring systems, especially if you have these 3D models already available. And I want to switch back to you, Marco.
And besides this and the great findings from the material scientific point of view, I want to point out something else, the productivity and economics aspect of use of nLIGHT's AFX. What you can see here is a realistic evaluation scenario of printing 9 turbine blades on our Aconity Midi Plus with a diameter of 250 millimeter in the building platform with a single laser AFX setup. And this served as a base for the time and cost distribution calculation. We considered 3 different parameter sets. So the standard parameter set of our facilities for nickel-based superalloy 718 with a 40 microns layer thickness and 80 microns Gaussian spot, as well as the AFX50 and AFX100 parameter set with a layer thickness of 50 and 100 microns respectively. So they were the outcome of the extensive parameter study last year. And what you can see here is that we were able to reduce the total build time from 70 hours with the standard parameter set to 30 hours with the AFX50 parameter set, with which we tuned our microstructure before. And if we use our AFX100 parameter set, we were even able to reduce the time up to 80%. And this, of course, has influence on your cost distribution. By looking at the volume costs per part, the standard parameter is around 10.5 euro per cubic centimeter, but using the AFX50 we can reduce it by around 45% and the AFX100 by around 75% of the costs. That's not the only interesting thing. Looking more detailed at the pie charts, if you can see the exposure time, if you reduce it, you of course reduce your costs, but then suddenly other aspects become more relevant to maybe optimize, like the material or add layer, which is a hint for the further optimization of your time and cost distribution. So I hope I was able to convey you that the use of AFX in combination with our machines offers a huge potential to not just only print parts, but to adjust the part properties on a macro as well as microscopic scale while maintaining part quality and with the advantages of the productivity and economics aspects. And if you can imagine, we are not at the end here, we are just at the beginning of exploiting those capabilities. And if you imagine a dual spot with the AFX, then the limits of the manipulation of the process and part properties is far from exhausted. Thank you.